What we need to talk about today is chemical formula. Chemical formulae, which is again, it's the plural of formula. There's a couple of very important things that we need to establish about chemical formula. Okay. Number one, we have to understand what it is, how we write down chemical formulae. Okay. So we know the atomic symbols, right? Like carbon, nitrogen, sulfur, oxygen, gold. For some reason, lead. Also for some reason, yeah. Okay, so these are all the atomic symbols, right? And we know about these. We've used these in class so far. Now what we need to understand is how we use them to show chemical reactions on paper, all right? So for instance, when we're writing a mathematics problem, okay? Mathematics. Or as they say in Britain, maths. Maths. Because mathematics is plural. We just say math, like idiots. But mathematics is plural. Okay? So mathematics, when you're writing a math problem, a maths problem, 4 times, I don't know, 16 divided by 38 all over 7. Right? That's a math problem. Or that is not even a problem, it's an equation. All right? So we can use numbers, which, fun little fact for you, which I've probably told you in classes before. These are Arabic numerals. These are Arabic numerals. These were invented by ancient Arabs. And also, fun fact for you, they're actually based on the number of angles in the symbols. Oh. 1, 2, 3, 4, 5.
Those lines under the line just ruined the whole system then.
6. Okay. Yeah, fun fact, those are Arabic numerals. We use them today. Yeah, anyway, because I would not want to be doing math. Well, it wouldn't really matter, but it would just take longer to write them out if you were using Roman numerals. What? 8 is like this. Here. And then I don't remember what 9 is. It's like.
Is it like?
It has a couple of extra things in it, but I don't remember.
300 right now. I want to see 300.
300 in what? In Roman numerals?
I want to see 300 angles.
Oh, 300 angles. Well, it was base 10.
Yeah.
Right. 300 in Roman would just be.
Yeah, but Arabic it would just be the 3.
It would just be 3 and 0, 0. Yeah. And a 0 has no angles. Yeah. Right? So there you go. That's why we use the number. Anyway. Just Google Arabic number set. Or like ancient Arabic numerals, something like that. I mean, we could use Roman numerals, it would be a pain.
Yeah.
Because
like 9s and stuff like that.
well, 9s aren't too bad. 8s are the worst. Right?
Oh, yeah.
8. Or if you start getting into like bigger numbers, like here 1,000. 500, and it's here. No, X. Okay. Anyone know what that number is?
I want to say it's.
I'll give you a hint. It's on the bottom of the all-seeing eye pyramid on a $1 bill. 1776. This is how actually I taught myself Roman numerals. Because it has every digit of the Roman numeral system. 1,000, 500, 100, 50, 10, 5, 1. Kind of fun. Anyway. Interesting. Anyway, that was kind of a tangent. So when we talk about chemical formulae, well, let's talk about algebra, right? Or even physics, right? So for those of you who have taken my astronomy course, you might recall this equation. G equals big G M1 times M2 all over R squared.
I know that.
Okay? This is an equation without any numbers. Well, there's a couple of numbers, right? There's a 2 here, a 1 here, a 2 there. Okay? But that doesn't mean that it is meaningless. These letters simply represent certain values that we can put into the equation, right? So in a chemical formula, this is, by the way, the universal law of gravitation. Of G. That's not a G. Nope, still not good. There we go. All right. The G is melting, yeah. The universal law of gravitation is an equation, but when we talk about chemistry, we look at something like this, okay? Okay? This is a chemical equation or chemical formula.
Is that a gradient sign or an arrow?
It's an arrow.
That's an arrow.
It's supposed to be.
Just stop. Just erase it.
Let it go. Let it go. It's so much worse.
It's an arrow. All right? Okay. So, could anyone tell me what is going on with this in terms of our chemicals that are going on? So there's water, right? There's the classic H2O.
And also CO2.
CO2, it's something that we are familiar with, right? Carbon dioxide. O2, this is oxygen. Okay? This guy has a special name that I don't expect you to know just off the top of your head. This is methane.
Yeah, it's totally got that with the CH.
So that's where carbon atoms and 4 hydrogen.
So this is 1 carbon and 4 hydrogens bonded together in 1 molecule.
Okay, so the exponent thing, yeah, that's not exponent. That
This subscript,
okay, yeah, that only affects the nearest one.
it only affects the letter or the atomic symbol after which it appears.
Okay.
Okay.
Even if they're like together like that.
Even if they're together. Yeah. So there's 1. Okay. You need retakes? Okay, all right, go. All right, so 1 carbon, 4 hydrogens. What is this? What is this guy? There's 2 oxygens. There's 2 oxygen atoms in a single molecule, right? What about water?
There's one hydrogen, no, there's
2 hydrogens, 1 oxygen.
Oh.
Remember, the number only applies to the letter after which it occurs. And this one is 1 carbon and 2 oxygens. Looks like a 20. It's supposed to be an O. It's the problem with O and 0, right? Okay, so we have this equation. Okay? So when we talk about this, we can also let's look at the same equation. And just for funsies, we're going to change the color of our thing. Okay? CH4 plus O. Oh shoot, that's not an O. That's a 2.
Is this the same one?
Yeah, we're just going to look at it.
Wow. Oh.
Better, right? Better. CH4. All right. H
My arrow is
2
almost up to.
O plus. Nope, I have not calibrated this board. Plus.
None of us got through it. We're almost there.
Okay. So here is what's interesting. So if we go back here, how many hydrogen atoms are on the left side of the equation? How many hydrogen atoms are on the right side of the equation? This is a problem. Because the hydrogen atoms have to go somewhere. Okay? So on the left side, we have what are called the reactants. And on the right side, we have the products. The reactants. All right, so on the left side of the equation, we have reactants. On the right side of the equation, we have products, okay? When the reactants react, right, they produce things, all right? Pretty straightforward. Okay, so reactants are going to products. Here's a very important thing, okay? Here's a really important thing. The number, gosh dang it, the number of atoms in the reactants must be equal. So I'm just going to put R here. R must be equal to P number of atoms.
They have to be equal to each other.
They need to be equal.
Oh.
This has to do with what's called the law of conservation of matter. Okay? We can't just have things disappear.
Also, an oxygen has
Also, we actually gain extra oxygen, right? Because there's
Oh, yeah.
2 oxygens on the right side, and then there's 3 oxygens on the right, or sorry, on the left side. So we need to do what is called balancing this equation, balancing this formula. Okay, so we're going to continue to work with the same problem, same formula.
Pardon the interruption. 7th through 9th grade, they are ready for you for pictures. Please go to the 3rd floor, 7th through 9th grade.
Okay,
Thank you.
so CH4 plus, and I know you're going to get tired of writing this out. Okay? So what we do in chemistry is we can add numbers here before the molecule to change the number of molecules. Okay? So in this case, we end up with what? So CH4 plus O2 equals H2O plus CO2, okay? How are we going to balance this? So we have, on this side, we have a total of 1 carbon. We have 4 hydrogens, and we have 2 oxygens, 2 oxygen atoms. And on this side, we have 1 carbon. We have 2 hydrogens. Sorry, 2 hydrogens. And how many oxygens do we have? 3.
Oh, yeah.
We have 3 oxygens on this side. So something has gone awry. Okay? This is not equal to that. And this is not equal to that. So how are we going to change? How are we going to balance this by changing the number of molecules in our equation?
So you can change the reactants. So we need more oxygen, less hydrogen.
We need more oxygen and fewer. Okay. So let's see here. How are we going to do this? Well, if we go, how about if we, let's just mess around here. Let's go back to the color black. So first thing that I think that we should do is put a 2 here. 2 H2O. That makes it so we have 4 hydrogens. But that also means that we have 4 oxygens. Right? Because 2 H2O means that there are 2 molecules of this. So that's 2 times 2. And we have 4 oxygens because there's 2 oxygens in the carbon dioxide, and then there's 1 oxygen in each of the 2 water molecules.
Yeah, like get rid of the water.
We have to get rid of a water molecule?
Well, basically, like you need to get rid of 2 hydrogen, or no, you get added.
No, watch.
Oh, the 2 right there. Oh,
Do you see how that works? That is legal. I shall allow it. Okay? Do we see how we have created a balanced equation? Sure. So I'm going to rewrite it in a less messy way. I told you were going to get tired of writing this equation. 2 O2. 2 H2O plus CO2. So what is this telling us? What is this equation telling us? Who could give me a synopsis of words of how this is working? Davis? I know you're just dying.
I'm really not.
Davis is not dying to tell me. Brendan? No, thank you. Layton?
Well, it looks to me like it was equal to, and then we just changed it just a little bit. We added a few molecules, added.
Yeah, so Layton says that we have added some molecules and now it's balanced, and that is true. Here is what I'm looking for here. We are reacting one methane with 2 oxygen molecules. That produces 2 water molecules and 1 carbon dioxide molecule. Okay? So the numbers at the front here, these guys change the number of molecules. Number of molecules. And this changes the number of atoms in a molecule. Does that make sense? More or less? So the number that goes, the subscript numbers that go next to the atomic symbol are the number of atoms in a molecule.
This is just like the sum we have in the quarter, like it's So I have a question.
Kind of, yeah.
Why wouldn't we just change the O2 to an O4?
Okay, that's an excellent question, Sir Benjamin. And the question for everyone watching at home is, why can't we just change the O2 to O4 instead of 2O2? Because this is not how the oxygen molecule works. All right? Oxygen only binds to itself. You get an oxygen, and they double bind to each other to make a molecule. They cannot bind in any other fashion. It makes a double covalent bond. Okay? You cannot change, that's actually a really good question. And I remember very specifically in my chemistry class when I was sitting in your seat, well, rather I was sitting in a different seat in Springville High School in the year 2005.
I was born of chemistry the year.
I took chemistry the year that you were born. It's like it was meant to be.
Yeah.
Okay, I am 30. I am double your age. Okay?
That was Don Stark.
So, okay? So I remember in my chemistry class, my chemistry teacher saying, you cannot change this number. I did. He was brutal to me, but I liked it.
Well, was that the guy that was really mean?
He wasn't mean. He would just make sure that I was the butt of every single joke. Because I was the kid that he chose in that class period to just relentlessly harass. Yeah. Okay, so when you are given a subscript of the number of atoms in a molecule, you cannot change that. You can, however, change the number of molecules in order to balance the equation. Okay? And this is a very simple example. We're going to do more intense examples later on. Right now, what I want to do is teach you how we name the nomenclature of chemistry. Okay? The nomenclature of chemistry. So, when we talk about molecules, molecules have names, right? Just like atoms have specific names. So let's look at an example. Should probably make that C bigger. Okay, this is what element? Potassium.
Are you serious? I was right.
Yep.
Woo!
Potassium.
And you can.
I mean, I'm a genius.
K, and that's in potassium.
And this is what?
Yeah.
Cl.
Chlorine.
Chlorine.
That would make sense
I
though.
like nothing.
All right, KCl. The name of this molecule is potassium. Oh, geez. That's not supposed to be this. Potassium. Potassium chloride. Oh, shoot. I screwed that up, but whatever. Chloride. CHLORIDE. Potassium chloride. So,
Looks like Casey.
what?
Potassium chloride.
Oh, yeah, no, it's KCl.
What was like the nomenclature?
Chemistry? Chemical nomenclature. So potassium chloride, all right? So when we're talking about molecules that are bonded together, you say the first name, okay? Especially in, well, in ionic bonds, but that's what we're talking about right now, so don't worry about it. You say the name of the first atom, and then the name of the second atom, but I don't say potassium chloride. It's, you take the first syllable of the name and put it in I. Okay, potassium chloride. All right? You may have also heard of sodium chloride, right? Well, let's look at some more interesting, well, maybe not interesting, but more complex examples. Okay? So let's talk about our good old friend. What is the name of this? CO2, what is the name of the molecule? Carbon dioxide. You, my friends, have been saying the name of a molecule without even understanding what the rules were. CO2, carbon, right? Carbon, dioxide.
Oh, I get it.
Oxygen.
No, I get it. I do. I promise I do.
Okay? What about this one? Does anyone recognize this molecule? Carbon what?
Carbon dioxide.
Carbon
monoxide.
You are so
Carbon
close.
oxide.
OxyClean.
Carbon
monoxide.
Somebody said that.
monoxide.
Somebody said
I
that.
said that. That's what I said.
I think I can.
That's what I said.
No, I totally
That's
said
what I
that.
said.
I'm
Like,
not-
Carbon monoxide. Okay? So the rule is we have prefixes for the number. Okay? So 1 is mon or mono. 2 is di. 3 is, anyone want to guess? Tri.
I was just gonna say,
Quad? Nope. Tetra.
and then
And penta.
oh my, I would have guessed that one too. It just had to break.
They're like different because
Why is it called Tetra?
Tetra. Sorry. Tetra. Like a tetrahedron. Yeah. Tetrahedron. Tetrahedron? I don't know. Okay. So you use these prefixes in the name of chemicals, in the name of molecules, to indicate the number of those molecules.
Is there any with a pentamolecule?
Are there any molecules that have penta in them? Oh yeah, absolutely.
How about 6?
6. So yes, there is hexa and hepta, which is 7, octa and nona and desa. But we're not going to see molecules that have those prefixes very often.
What is the highest?
What is the highest? So you would start adding, so like desa, you know,
No, like no, what is the highest?
okay, so you can make a name for, so for instance, like million, billion, trillion, quadrillion, right? All of these. So when we talk about something that has a quadrillion, quadrillion, quintillion, sextillion, septillion, octillion, nonillion, decillion, and then you start using more words. So decimillion, decibillion, decitrillion. So you start just putting the numbers together. Decitrillion, yeah, it's a lot. All right, so I want you to tell me what the name of this element of this molecule is. Magnesium Fahrenheit. No. Magnesium fluoride.
I said that.
No.
Magnesium difluoride.
Magnesium difluoride. Not Magna. Magna is a city that you never want to visit.
Like that's an actual.
Magna? Yeah, Magna, Utah. Magnesium.
why is like some of them the G is like smaller, but on this one it's like the same size?
Okay, that's a great question. Magnesium difluoride. Magnesium difluoride. Okay, so Shelby asked the question, why in this equation do we have an M, a big M, small g,
I think I figured it out.
and in this equation we have 2 big letters? Why? Yeah, Ben.
Because the smaller one always follows an element, so you can tell it's the same elements.
Right.
So if it was like just M and like a capital F, it would be two different.
Right. So the capital letters indicate a different atom, a different element. Okay. Mg is different from Mn. Mn is manganese. Mg is magnesium.
Wait, that's so true.
I kind of figured it out, like, once I asked the question.
That's why I ask questions, though. Yeah, Franklin.
What is ACL? That's two different capital letters in the same element.
AC what?
L. It's right by RAFR.
Oh, no. This indicates that this is actually not there. It's actually a part of the actual thing. So this is these right here are just placeholders.
Huh?
I love
Yeah,
that.
they just have placeholders for the charts because they don't.
Oh, wait,
have to
didn't
double
that
chart.
one guy put like pieces in there?
Mendeley.
That's what I like saw when I did that thingy.
Yep.
It's not-
Okay, so magnesium difluoride.
It's totally know you're doing this now that you've convinced.
Okay, what about this? What about this molecule? What is the name of that molecule?
Water.
Would it be di?
Dihydrogen hydrogen
Oxide.
monoxide.
I forgot that you still have to follow.
That's
So
what this is.
that's what that is. So when it's the first element in the molecule, you don't need to use mon or mono. You don't need to use it, right? It's just magnesium. Okay? But if it is the second element, you do need to indicate the number, no matter what, even if the number is 1. So this is dihydrogen monoxide. Yeah. It's a great question. It's a great question, Hannah. But what about this one? What about potassium chloride? Okay, if they are both just single, it is potassium chloride. You don't have to say potassium monochloride, and you don't have to say monopotassium monochloride.
Lines like
There's
this.
just like a five any molecule that's over space.
Yep, if both halves are single, you just say the name of the first element and then the first syllable of the second element followed by I. Mono, or well, so in oxygen, you could say monoxide, but that's a little bit redundant. Monoxide is easier.
I have a question.
What's your question?
About chemistry, it's not about this, but I just thought, and it's very important.
Okay.
Are there any elements that don't have isotopes? Because there's those ones up there, and I know you explained because we can't fully tell because they're so dangerous and stuff, but then they're just in parentheses, right?
Right.
But is there potential that they just don't have an isotope?
So they don't really have isotopes. So you're looking at like RF,
Yeah.
yeah, and all those grayed out ones. They don't actually really have isotopes because an isotope, by definition, is naturally occurring.
Yeah.
Right? So, like, rubidium has a whole bunch of different isotopes. You can see its average atomic mass is 85.46. That's an average. I think there's like 6 different commonly occurring isotopes of rubidium. Okay. But there's only like 3 commonly occurring isotopes of carbon, right? And we only really consider those 3. It can happen that every once in a while you'll end up seeing really briefly like a carbon 17 or something like that. but it is so short-lived that we don't really consider it a major isotope.
And that's what happens with them.
They're small.
That's what?
So that's what happens with them. Like there is, but they happen so fast that they're not even really considered an isotope.
Right.
Okay. So they could potentially just have whole numbers.
Yeah, they could, but again, they really only have whole numbers because we just make them in a lab.
Yeah.
Yes, U is 92, bottom, uranium. You can spell all sorts of things with those. All right. So, questions on chemical formula or chemical nomenclature so far? Chemical nomenclature gets way more complicated, but I don't want to get into it. Okay?
Is
Yeah.
there ever a time when it would be like H10, or will that not really happen? And if it does, would we put like monohydrogen monoxide?
So there is H2O2,
Yeah.
which is hydrogen peroxide, but that is obeying a different set of rules, and we'll get into that later.
So there,
H2O2, it's just one more.
Yeah,
It has only one more oxygen. Yeah, so like Shelley brings up a good point. Have any of you used hydrogen peroxide to like clean out canker sores in your mouth or something like that? I definitely wouldn't recommend drinking it because if you drink more than just a little bit, it can be fatal. So, but hydrogen peroxide and dihydrogen monoxide are very close to each other. Molecular in their molecular shape and the number of atoms they have, just one has one oxygen more, but it behaves very differently, right? That's a chemical property. It reacts different with different things, right? Just like we've talked about before, that sodium by itself explodes when it touches air, right? And chlorine by itself will literally melt your lungs. But sodium chloride, when they're together, you just put it on your steak and it's delicious.
which is so weird.
Or what?
I
Chlorine?
guess you don't have to have your lungs.
So chlorine in a pool is bonded to the oxygen in the water. So it makes chlorinated water. So it doesn't exist just as chlorine in the water. It binds to the molecules in the water.
So what would it be?
When it's bonded together. So it's not just like you have some chlorine atoms in there. You do H2O plus Cl, and that creates, well, pool water, yeah. So you put a very small amount of chlorine, and it reacts with the hydrogen and the oxygen, and what it actually does is it creates Cl or hydrogen chloride. It does plus O2. Oh, shoot. It's supposed to be So what it actually does is there's a chemical reaction where it makes a small amount of hydrochloric acid and pure oxygen. And the hydrochloric acid is such a small percentage of like what you're swimming in that it kills the bacteria and so forth and the viruses, but it won't kill you. It's not great for your skin, and it bleaches your hair, right? Yeah. You've ever seen someone who's like on a swimming team if they have blonde hair? So my wife, it turns green. Yeah. So my wife's hair. My wife was a high school state champion swimmer, and she had green hair for more portions of her
My
high
hair was
school.
like more blonde. I think it was like last summer. My hair turned green.
Yeah, and she spent enough time in chlorinated water.
So how do they get chlorine in there? Isn't it
They're like little tablets.
Yeah, so you do a tablet and you put it into the pool, and then there's another reaction that gets it to the chlorine gas, and then it reacts with the water before it comes out.
It's a little tablet, just like straight chlorine.
No. Because chlorine by itself exists as a gas at room temperature and pressure. Okay, good questions, y'all. So we only have a few minutes left. I'm going to end the video here.
I'd like to.
You put it